Welcome to the deep dive. Have you ever stood under a huge bridge or watched one of those massive cranes lifting something heavy? Or maybe even just put a big stack of books on a shelf and thought, what's really going on inside that thing?
Hmm.
Beyond what you can see, there's this whole hidden world of forces keeping things together. Or, well, sometimes not, if things go wrong. So, our mission today is to kind of pull back the curtain. We want to show you how engineers figure out these invisible forces inside structures. We're talking about the really crucial hidden internal loads. They decide if a skyscraper beam holds up or if a bridge cable can handle, wind and traffic. And understanding this stuff isn't just for engineers. It gives you real insight into how basically everything around us is built. Today, we're going to try and give you a shortcut through some topics that sound pretty dense. Things like the method of sections, shear and moment diagrams, even how cables behave, which is actually fascinating. We're aiming to turn that textbook jargon into, real aha moments. Give you some surprising facts and a clear way to feel genuinely clued in about the structures you use every day. So let's imagine. Imagine we have to design a new footbridge, maybe over a river. It needs to be light, but super strong, right? For lots of people. Where do we even begin with that?
Yeah, that's a great place to start. Because honestly, to design any structural part correctly, your bridge, a shelf, whatever, you absolutely have to know the loads acting inside it. It's not just about the weight sitting on top. It's predicting how the material itself responds internally, making sure it can resist those pressures safely. Think of it like understanding the stress points in a muscle before you ask it to lift something heavy.
Yeah.
You need to know what's happening within.
Oh, I like that muscle analogy. So it's not just the external push or pull, it's predicting where those internal sort of fibers are straining the most. And that brings us to the method of sections, right? Sounds dramatic.
It does a bit.
But it's really just about taking an imaginary slice, isn't it? So for our footbridge beam, if we want to know the forces at one specific spot, we just imagine cutting it
Yeah.
perpendicular to its length right through that point.
Yeah. Exactly. You make this imaginary cut. And when you do that, those internal loads that were hidden before, they suddenly get, well, exposed.
Yeah.
They act like external forces on the two pieces you've mentally separated. It's the slicing an apple to see the core. The forces holding it together become visible, in a way, on that cut surface.
Okay, so we slice our bridge beam in our minds. What do we actually see there? In 2D, you said there are usually three key things.
That's right. Three main internal loadings in two dimensions. First up is the normal force. We call it N. It acts perpendicular straight into or out of the cut surface. It's what stops the two pieces from pulling apart.
That's tension.
Right, tension, which we usually call positive.
Uh-huh.
Or it stops them from squishing together, which is compression.
So stretching or squishing along the beam's length. Got it. What's next?
Then you've got shear force, V. This one acts tangent to the cut surface, like scissors trying to slice the beam sideways. It's the force that wants to make one part slide past the other vertically. Crucial for designing things like bolts or welds. They have to resist that shear.
Ah, okay. Like a cutting force. And the third one?
The bending moment, M. This isn't a direct push or pull. It's a rotational force, technically a couple moment. It's what tries to actually bend the beam. A positive bending moment usually means it bends kind of concave up, like a smile. If you think about our bridge deck.
So it could sag down or arch up slightly?
Exactly. And understanding this tells engineers where to put reinforcement, like rebar and concrete. Because one side of the bent beam is getting compressed, the other side is stretched. M prevents one part from just sort of rotating away from the other, keeps it bending together.
Makes sense. So normal force, shear force, bending moment, NVM.
Precisely. And just quickly, if you're in three dimensions, it gets a bit more complex. You'd also have twisting forces, torsional moments, and shear and bending in multiple directions. But the basic idea of cutting and exposing the internal forces, the method of sections, still works. Just more math involved.
Okay, so how do we actually calculate N, V, and M once we've made our imaginary cut?
Well, first, you might need to figure out the external support reactions for the whole structure, like how the piers are holding up our bridge, basic statics.
Right, the overall forces.
Then you draw what's called a free body diagram. But just for one of the cut pieces, usually you pick the simpler piece, the one with fewer external forces acting on it. Just makes life easier.
And then?
Then you apply the equations of equilibrium. That fundamental physics thing, sum of forces equals zero, sum of moments equals zero. You apply those equations to your free body diagram, and that lets you solve for the unknowns, which are your internal N, V, and M at the cut.
Okay, that sounds logical, like balancing the books for forces.
It is, exactly. And here's a neat practical example of why this matters. Think about, say, a backhoe arm linkage. or even a connecting rod in an engine. If you make those parts curvy, it's actually less efficient structurally. They end up dealing with bending and axial load.
Ah, so making them straight is better.
Much better design, yes. If they're straight members loaded at the ends, they mostly just experience axial force tension or compression. They avoid most of that complex bending stress. It's cleaner, more efficient.
Interesting.
Another one is like a shop crane. You see how they often have extra plates or thicker sections around the joints?
Yeah, where things connect.
That's not guesswork. Designers use the method of sections to figure out that the internal bending moments get really high near those joints when lifting a heavy load, so they add reinforcement right there. Knowing the internal forces tells them exactly where the critical spots are.
So for our footbridge, this method would tell us precisely where in the main beam, say, the compression is highest, or where the bending is most severe under load.
Exactly. It pinpoints those critical internal stresses at a specific location.
Okay, but knowing the forces at one point is useful, but probably not enough, right? How do engineers see the bigger picture? Like how these forces change along the whole beam?
Ah, good question. Because you're right, it often varies significantly. That's where we need to visualize the invisible across the entire member. And for that, we use shear and moment diagrams.
Diagrams, okay, graphical tool.
Powerful graphical tools, yes. They show engineers exactly how the shear force, V, and the bending moment, M, change from one end of the beam to the other. This is absolutely vital for design, especially for something like our bridge where loads might move around. You need the full picture.
So how do you make these diagrams? Is it just lots of method of sections cuts?
You could do that, but it would be incredibly tedious. The standard way is a bit more clever. Instead of cutting at one specific spot, you cut at an arbitrary distance, let's call it X, from one end.
Okay, so X can be anywhere along the beam.
Right. Then you apply the equilibrium equations just like before, but you do it for that segment of length X. This gives you equations for V and M as functions of X, so Vx and M. These equations describe the shear and moment at any point X.
Ah, I see. A formula for the force at any location.
Exactly. Now, one tricky bit is that these functions, Vx and Mx, might suddenly change, or their slopes might change abruptly. This happens wherever you have, say, a concentrated load hitting the beam, like a heavy lamppost on our bridge, or a support point, or where a distributed load starts or stops.
So you might need different equations for different sections of the beam?
Often, yes. You end up with piecewise functions. You'll have one set of Vx and Mx equations for, say, the first part of the beam, then another set for the next part, and so on. Then you plot these equations, and that gives you the complete diagrams.
And these diagrams. What's the big payoff for our bridge?
Huge payoff is efficient design. Think about those big steel girders you see on bridges sometimes, the ones that are deeper near the piers and shallower in the middle.
Yeah, tapered girders.
That shape comes directly from the moment diagram. The diagram shows the internal bending moment is usually way bigger near the supports and smaller out in the middle of the span. So engineers make the girder deeper where the moment is high and shallower where it's low. Saves a ton of material, which means less weight, less cost for our bridge.
But still safe because the strength is where it's needed most.
Precisely. It's design optimization in action. The diagrams are like, I don't know, a stress map or an X-ray for the beam. They guide engineers to put the strength exactly where it needs to be.
Okay, that's really cool. But calculating Vx and Mx by sectioning at X still sounds like it could involve some fairly involved algebra.
It can, especially for complex loading. But here's where it gets really elegant. There are these amazing relationships, differential relationships between the load, the shear, and the moment. These provide a massive shortcut for constructing the diagrams. Much faster, much more intuitive once you get the hang of it.
Ooh, shortcuts. Tell me more.
Okay, let's start with load and shear. The slope of the shear diagram, the V diagram, at any point along the beam is equal to the value of the distributed load acting on the beam at that point.
Wait, the slope of the shear graph equals the load.
Yep. If the load is pushing down, which we often call negative, the shear diagram slopes downwards. If the load pushes up, the shear diagram slopes upwards. It's a direct link.
Huh. Okay.
And even more useful, the change in shear between any 2 points on the beam is equal to the area under the loading diagram between those same 2 points.
Area under the load curve equals change in shear. Okay.
Think about a concentrated force like that service truck on our bridge. A concentrated downward force makes the shear diagram suddenly jump downwards by exactly the amount of that force.
A jump. Okay, that's very visual.
It really is. Now let's look at shear and moment. Same kind of relationship, just shifted one step. The slope of the moment diagram, the M diagram, at any point is equal to the value of the shear force at that point.
So slope of moment equals shear value.
Right. If the shear V is positive, the moment diagram M slopes upwards. If V is negative, M slopes downwards.
And the area thing works too.
You got it. The change in moment between any 2 points is equal to the area under the shear diagram between those points.
Wow. So load dictates the slope of shear, and area under load gives change in shear. Then shear dictates the slope of moment, and area under shear gives change in moment.
Exactly. It's this beautiful cascade. Each diagram mathematically builds the next one.
Is there a jump case for moment too?
There is. If you have a concentrated couple moment acting on the beam, maybe from a stiff bolted connection, the shear diagram isn't affected directly. But the moment diagram will suddenly jump at that point. A clockwise couple moment usually makes it jump upwards by the amount of that moment.
Okay. These relationships seem incredibly powerful for drawing the diagrams quickly.
They are. But here's probably the most critical takeaway from all this, especially for design.
What's that?
Remember how the slope of the moment diagram is equal to the shear? Well, think about calculus. When does a curve reach a maximum or minimum value?
When its slope is 0.
Bingo. So if the slope of the moment diagram M is 0, that means the shear force V must be 0 at that point. This tells us something absolutely crucial. A maximum bending moment, either positive or negative maximum, occurs wherever the shear force is equal to 0.
So you look at the shear diagram, find where it crosses the 0 line.
Yes,
And you know that right at that point on the beam, the bending moment is at a peak value.
exactly. And since bending moment often relates directly to the maximum stress in the beam material, finding where V at 0 instantly tells engineers where the most critical point for bending failure is likely to be.
That's huge. That's like the beam's weak spot, revealed by the math.
It really is. It allows engineers to pinpoint exactly where the beam needs to be strongest, potentially saving material elsewhere. It's incredibly efficient.
And there was something about polynomials, too, like the shapes of the curves.
Right. Because of these slope and area relationships, the degree of the curves increases.
Yeah.
If your distributed load is, say, constant, a 0-degree polynomial,
Like just uniform weights.
yeah, then the shear diagram will be a sloping straight line, a first-degree polynomial, or linear,
Okay.
and the moment diagram will be a parabola, a second-degree polynomial, or quadratic. If the load was linear, shear would be quadratic, and moment would be cubic. Each step goes up 1 degree.
So there's this hidden mathematical structure dictating the internal forces. It's not just random.
Not at all. It's very predictable, very elegant, actually. These relationships let engineers rapidly sketch the shapes of the shear and moment diagrams and find those critical maximum values without tons of calculation. Like a doctor reading an X-ray, you learn to spot the important features quickly.
Okay, that covers beams pretty well.
Yeah.
Let's switch gears a bit. What about structures that aren't rigid beams? What about like flexible cables and chains? They're used everywhere too. Suspension bridges, power lines.
Absolutely. Cables are fascinating. They combine incredible strength with lightness and flexibility. We're moving into, as you said, the art of the hang.
So what are the key things engineers assume about cables?
2 main simplifying assumptions, usually. First, they're considered perfectly flexible. This means they offer basically 0 resistance to bending. The consequence is that the tensile force inside the cable always acts perfectly tangent to the cable's curve at any point. It just pulls along the line of the cable.
No bending stiffness.
Okay.
And
They're considered inextensible, meaning their length doesn't change under load. Now, real cables do stretch a tiny bit, but for many calculations, it's assuming constant length simplifies things hugely without much loss of accuracy.
got it. Flexible and non-stretchy. So how do they behave under load? Let's take simple cases first. What if a cable just supports a few distinct weights, like traffic lights hanging from a wire?
Right. Cables with concentrated loads, where we can often ignore the cable's own weight. In that case, the cable forms a series of straight-line segments between the load points and the supports.
Straight lines, not curves.
Between the loads, yes. Each straight segment has a constant tension force acting along it. The shape is determined by the position and magnitude of the loads.
And where's the tension highest in that kind of setup?
Good question. The maximum tension will always be in the segment that has the steepest slope, the one pulling up most sharply towards the support. Makes sense, right? It's working hardest against gravity.
Yeah, that feels intuitive. Okay, what about more complex loads, like distributed loads? Think suspension bridges. The main cables hold up the roadway, which is a pretty uniform weight spread out horizontally.
Right. That's our second key scenario. If a cable supports a load that's uniformly distributed horizontally like that bridge deck, and we again assume the cable's own weight is negligible compared to the deck,
Yeah.
then the shape the cable takes is a perfect parabola.
A parabola, like the flight of a ball.
Exactly, that mathematical shape. And here's a really critical point for suspension bridge design. The horizontal component of the tension in that parabolic cable is constant everywhere along its length. Only the vertical component changes.
Ugh. FH is constant. That must simplify calculations.
Immensely. It's fundamental to analyzing suspension bridges. Those iconic curves you see are parabolas because the load, the deck, is uniform horizontally.
Okay, but what if the cable's own weight is the main load, like those big power lines sagging between towers? That weight isn't distributed horizontally, is it? It's spread along the cable itself.
Precisely. That's the third scenario. When the load is the cable's own weight, it's distributed along the arc length of the cable. And this results in a different curve.
Not a parabola.
Nope. It forms a catenary curve. It looks a bit like a parabola, but it's mathematically distinct, described by hyperbolic cosine functions.
Catenary. Okay. Sounds more complicated.
It is mathematically. Calculating the exact shape, tension, and length of a catenary involves more complex equations.
Is there another shortcut? Because calculating catenaries for every power line span seems like a nightmare.
Yeah, there is. And this is a really neat insight from the source material. It turns out that if the sag of the cable is small compared to its span length, which is often true for power lines, they don't usually droop that dramatically,
Right.
then the catenary curve can be very accurately approximated by a parabola.
Really? So you can use the simpler parabola math even for self-weight if the sag isn't too big?
For many practical engineering purposes, yes. You can often treat the cable's weight as if it were uniformly distributed horizontally and use the parabola equations. It's a fantastic simplification that saves enormous amounts of calculation time while still being safe for most typical designs.
Wow, that's a great example of practical engineering judgment, balancing accuracy and complexity.
It absolutely is. It shows how engineers leverage mathematical understanding to find efficient, workable solutions for real-world problems.
So the next time I see power lines sagging or look at a suspension bridge, I can appreciate those specific curves, parabolic or catenary, knowing they're the precise shapes needed to handle the forces involved.
Exactly. They're not arbitrary shapes. They're dictated by physics and the loads they carry.
Well, this has been quite the journey. We've gone from thinking about a simple shelf to diving deep into the hidden world inside structures. We started with that imaginary cut, the method of sections, to expose internal forces like N, V, and M in our bridge beam.
Then we visualized how those forces change along the entire beam using shear and moment diagrams, learning those cool shortcut relationships between load, shear, and moment.
And finding that critical point where shear is zero, telling us where the maximum bending moment lurks. And finally, we explored the elegance of cables, seeing how they form straight lines, parabolas, or catenaries depending on the load.
So hopefully you listening now have a much better feel for these core concepts. They really do underpin the design of almost everything structural around us.
From a tiny bracket holding up a sign to, yeah, those massive bridges, these principles of internal forces are always at work, silently keeping things stable.
It's all about balancing those internal stresses against the external loads.
So here's a thought to leave you with. Start looking around at everyday objects. Your chair, a bicycle frame, maybe a ladder, a bookshelf. Think about where the loads are and try to imagine those internal forces, the tension, compression, shear, bending working inside. Where might the stresses be highest?
Yeah, where might a designer have needed to add a bit more material or choose a specific shape?
The next time you cross a bridge or see a crane, remember that symphony of internal forces playing out beneath the surface. It's all carefully calculated, precisely balanced.
That understanding allows engineers to build our world, basically one well-designed component at a time.
So the question is, what other hidden forces, what other invisible systems are shaping the world you interact with every single day? Something to ponder.